There are four kinds of statement in SystemVerilog that refer to the use of properties. They are the assert statement, cover statement, assume statement and restrict statement. And these four statements are generically known as concurrent assertions. And arguably that's a bit of a misnomer. Perhaps we should only call the assert statement an assertion, but nonetheless generically these four are all known as concurrent assertions. An assert statement asserts that a particular property must hold in every single clock cycle. The property must always be true. A cover statement, on the other hand, asserts that a property must hold in at least one clock cycle. And the cover statement gets interpreted slightly differently for simulation versus formal verification. So with a simulator, if you write a cover property, the simulator is going to count the number of times that that property holds during simulation. Whereas for formal verification, the formal tool will attempt to prove that that property holds at least once, that there is some circumstance in which that property will hold, and a formal tool would typically generate what's called a witness trace to show you a particular case where that property holds. So with assert, the property must hold in every cycle. With cover, the property must hold under at least one particular circumstance. And the remaining two statements, assume and restrict, are used to define constraints on the input of the logic being verified for the sake of formal verification. So assume and restrict primarily exist for the purposes of formal verification. They constrain the inputs to the block of logic being tested. But nonetheless, they can still be used in the simulator. And the difference is that with an assume, the simulator would treat the assume as being equivalent to an assert. So for simulation, assert and assume are effectively treated the same way. And with restrict, a simulator would typically ignore restrict. So assumes are treated like asserts for simulation, restricts are typically ignored by simulation, assume and restrict are treated in the same way for formal, they're used to constrain the inputs. Let's look at the typical or canonical concurrent assertion. This is what a typical concurrent assertion would look like in its entirety. First of all, it's a really good idea to label every concurrent assertion. The label is actually an optional part of the syntax, but it's really good practice to label the concurrent assertion, because if you label an assertion, then it's much easier to identify the property within the tool when it passes or fails. So do give every concurrent assertion a label. Then every concurrent assertion must have a sampling event, and that sampling event is typically the pos edge of clock or the neg edge of a clock. Assertions can actually have more than one sampling event, but so-called multi-clock assertions are outside the scope of this particular webinar. Then an assertion would typically contain an abort condition or a termination condition. The abort condition or termination condition typically names any resets or interrupts or any other signal that's going to mean that the assertion no longer need be checked. Think about a reset. A reset could typically go active at any point during the evaluation of an assertion. And if your assertion spans multiple clock cycles, as they typically will, then if the reset goes active halfway through the evaluation of the assertion, that typically means that all bets are off with respect to the validity of the assertion. So there's no point in checking that the right-hand side of an assertion holds after we've seen a reset. So you could code that up by naming the reset many times within the assertion, but it's typically much tidier to put signals like resets within the abort condition. So that's what we'll typically do. Then the main guts of the assertion typically makes use of an implication operator. On the left-hand side of the implication operator, we've got the antecedent or precondition, and then on the right-hand side of the implication operator, we've got the consequent or the post-condition. So what an assertion typically says is look for the antecedent, check to see when this condition occurs, and when the antecedent holds, check that the consequent holds, check that the right-hand side is true as well. So that's the typical form of a concurrent assertion. Concurrent assertions don't always have to look like that, and I'll point out the exceptions in a minute. then it's a really good idea to use the else part of an assertion to write out an error message in the case that the assertion fails. And SystemVerilog gives us a special system called $error specifically for that purpose. So here we can write out a message when the assertion fails and maybe print out the values of the variables that are being used in the assertion, so that it makes it easier to debug the assertion. Well, any values of variables or wires that are mentioned within an assertion, typically I should say outside of the disable clause, any variables mentioned here in the antecedent or the consequent, actually get sampled during the pre-pwned SystemVerilog scheduler region. That is, the variables here get sampled as we come into the current time step. And if you're then writing out the values of those variables in a message, it's a really good idea to write out the same values of the variables that were sampled and used within the assertion. And you can do that by calling the $sampled function within the error message that's being written out. If you don't use $sampled here, then the values of the variables that are written out will be the values as they were within the observed region of the SystemVerilog scheduler rather than the pre-pwned region of the SystemVerilog scheduler. So it's good practice to use $sampled here to make sure that we're writing out precisely the same values that were sampled and checked within the assertion.
Doulos is a training company providing expertise and specialist training worldwide in all of the areas you can see on screen, from SoC design and verification, FPGA and hardware design, to embedded software and Python and deep learning. You can watch the rest of John's webinar, become an SVA expert in 1 hour whenever you want, by heading over to our website www.doulos.com/od and registering for free. For more free tips and tutorials, visit the know-how area of our website, and don't forget to subscribe to our YouTube channel. Thanks for watching.